Okay. All right. Hello, everyone. Today I want to talk about not exoplanets because these things actually have data and more focus on brown dwarfs and how we can use brown dwarf spectra to learn more about exoplanets. And so I just want to kind of give you a tour of some of the things that we can do with, oh, Ty, I took your spot, by the way. He's here now. Yeah.
Exciting research is happening.
Anyway, yeah, figure out what brown dwarf spectra can tell us about their atmospheres and how we can use them as analogs for understanding transiting exoplanets. So what are brown dwarfs? Brown dwarfs are failed stars. They're stars that are not yet massive enough to fuse hydrogen, but in some cases are massive enough to have fused deuterium at some point in their lifetime. But they're more massive than so-called planets. And so generally, the boundary between stars and brown dwarfs tends to be around 75 or 80 Jupiter masses, and the boundary between planets and brown dwarfs tends to be 13 Jupiter masses or so, but that's all like wrong and fudgy, as the formation processes tend to overlap quite a bit. You can form low mass brown dwarfs possibly via gravitational instability, like you form stars and whatnot, or you could possibly form massive planets on the order of 5 Jupiter masses via some core accretion mechanism. So I think the debate is still out on that. So what's interesting about brown dwarfs is they effectively cool with time. So here's age down here, effective temperature up here. And for a given effective temperature of a brown dwarf, higher mass older objects can have the same temperature as, lower mass, let me start over. Higher mass older objects can have the same effective temperatures as younger lower mass objects. So that makes for somewhat of a degeneracy in the classification of these objects. One of the more common ways for characterizing brown dwarfs is by putting them on a color magnitude diagram, like what stellar astrophysicists do. And so you end up having this kind of brown dwarf sequence here, where you have M dwarfs up here, L dwarfs here, you have this L to T transition here, and then you have or mid-Ts here, and then you start rolling off into the early T dwarfs, so sort of in between these two objects in here, and then eventually you have Y dwarfs, which would be down here. So you can think of this as a temperature sequence. And so there's a whole lot of physics that goes into explaining this. Oh, I thought you were raising a hand. A whole lot of physics that goes into describing this color magnitude diagram. Anywhere from clouds to weird things like fingering convection can explain how you move around in this color space here. So what are some interesting questions that I want to answer or ask with brown dwarfs? Or what are their molecular abundances? A lot of brown dwarf interpretations has been borrowed from the stellar atmosphere community, where everything's about Fe over H. What is the metallicity? But we want to do better than that. If we can measure molecular abundances, can we say anything about their distributions in their atmospheres or vertical distributions? What can this tell us about chemical processes happening in their atmospheres? How do their elemental abundances compare to their host stars if they're companions? Does this tell us about how they formed? Did they form in the same molecular cloud, or did one form via some other mechanism? Would you expect differences in their abundances? What are their thermal structures? Can we tell if they're not in radiative convective equilibrium like we would expect? What are the observable properties of clouds? Are they patchy? Can we actually back out the cloud compositions? What are the sources and causes of variability? So there's a lot of observations of rotational variability of these brown dwarfs, which may be due to clouds or other interesting physical effects. And finally, if we study a large population of objects, what can we learn about the physics by looking at trends in, say, temperature or gravity? So again, brown dwarfs kind of lay the groundwork because of their richer, more voluminous data set. So it's a really good way of these are really good laboratories for understanding the same physics and chemistry that are happening in exoplanets. So here's just kind of an example, like sampler platter of the type of spectra that we have for brown dwarfs. So these are all observations ranging from M dwarfs all the way to very late T dwarfs, and you can just kind of see the evolution of various absorption features and how condensates evolve as you end up having like more water vapor absorption and things like methane as you cool off. So I'm going to ask, what can we learn from these spectra about the physical properties happening in their atmospheres? So the classic approach to inferring properties about brown dwarf atmospheres is the so-called grid modeling approach. Again, this has been borrowed from the stellar astrophysics community, where these models make all sorts of assumptions about the physics we think should be happening in the atmospheres, like radiative convective equilibrium, chemical equilibrium. Sometimes disequilibrium is taken into account, and that they're generally solar composition, maybe we can perturb that with the metallicity or something like that. And the parameters of interest are generally something like the effective temperature in log G, because we can tie that back to the revolution. And so usually what most observers do is they download Mark Marley's models or someone else's models, and they plot them up against the data that they take in some sort of grid modeling fashion, and they figure out what the best combination of log G and effective temperature is, and then they're happy. So that's great, except here's an example of a bunch of different types of stellar atmosphere models that give you different answers for the same object because of the different assumptions they're making. So you can get anywhere, for this particular object, you can get anywhere from an effective temperature of 1600 to 2000. So that's a 400 Kelvin difference, just simply due to the assumptions that are made in the model. So how do you know which one is right? You can see some of these models don't even really fit the data. So what does it even mean to back out an effective temperature of 2000 Kelvin when the model is not fitting the data? So I just kind of said that. So this is like what I do every day, and it makes me sad because it's just a lot of pushing a button. No, it's actually really exciting. So this is this inverse approach where instead of making these assumptions, we relax these assumptions and just ask, what does a spectrum actually care about? It doesn't give a crap how clouds are formed or what chemistry is happening in the atmosphere. It just cares about like the source function, the Planck function, or scattering in the atmosphere, and what the opacities are. So that's what we're going to try and back out. So can we back those pieces of information out? And the opacities, of course, depend on the abundances of the various molecules absorbing in their atmospheres. Brown dwarfs, unlike stars, they're cooler. So instead of having elemental opacities, they're really going to be dominated by molecular opacities, which makes it tricky to back out their abundances using classic methods. So that's why we're going to use this retrieval framework. And then we're going to ask, is there enough information in the spectra to be able to back out what the thermal structure is as a function of altitude, like we can do for the Earth? So Caroline, you already saw this talk, so feel free to take a nap. And so what you do is you have this closed loop here where you have these parameters you're interested in, properties of the atmosphere. Here's the physics that we're imposing. You sort of bin it down according to what the data you're comparing it to, and that all goes into some Bayesian magic that you evaluate with your favorite downloadable code thing. And so this just kind of give you an illustration of the where various gases and temperatures, where they matter in the spectra. Are you getting like a weird feedback from this, or is this okay? Okay. It's like water pretty much absorbs everywhere in the near infrared here. You have methane absorbing on the wing here. This is H-band. Ammonia absorbs in various places. So you can see that there are lever arms on the spectra for which we can actually back out the abundances of these various molecules. And we can get some handle on the thermal structure as well. So here's kind of a not real-time retrieval. I would be very happy if this were a real-time retrieval. But what's happening here is that Markov chain Monte Carlo is adjusting the thermal structure, and the abundance is not shown to fit this data. And so you can see that as we relaxed from this kind of isothermal atmosphere, there was enough information in the spectra to relax this to this thermal profile that is more or less consistent with radiative convective equilibrium. And note the spread and the possible thousands of spectra that can fit this data nearly equally well is very tiny, but there is a huge spread in the thermal structure. So that tells us there's inherent degeneracies in the thermal structure and the abundances. And I'm going to give you a quiz at the end of this talk on what the values of these numbers are. I'm just kidding. That would be awful. Point is, we can back out what the correlations and the abundances are for each of these molecules. And so we find that like methane and water, which are kind of the more dominant opacity sources in these particular objects, is correlated with gravity. So that's kind of like a mass gravity degeneracy that's been pointed out before. So you may have heard, like with retrieval approaches in exoplanets, that we get weird answers like the entire atmosphere can be made out of CO2 even though it's a hot Jupiter. We shouldn't believe these results kind of stuff. So that's why we check it on objects for which we think we know the answer. And so these are benchmark objects. These are objects, brown dwarfs that orbit host stars for which we've measured the abundances, like the metallicity and the C to O, and for which we know the age, albeit ages for stars can be somewhat sketchy if they're not in clusters. 3 to 12 gigayears is like spanning the entire age of the universe, so that's not really that useful. but this one is. And so Johanna Teskey, a collaborator on a lot of this work, has done a really good job of backing out what carbon to oxygen ratios are in the companion stars that these brown dwarfs are orbiting, and so we can use this as an extra dimension. So the idea is to see if we can get the same metallicity in the C to O and age via our retrieval method as what we get for the host star, because we would have expected them to form at the same time in the same clump of gas. So here's two objects for which we did this for. Yay, fits are good. And these are the thermal profiles that we get and the spread in those thermal profiles compared to a self-consistent model. And we find that over this gray region, which is the photosphere, where the observations are sensitive, we agree pretty well. Down here, you can't really believe that. Up here, there's some contribution, but I wouldn't really believe this up here either. And so we could back out what the abundances are. We can even check whether or not these objects are cloudy by including or not including clouds. And we find that whether or not you include clouds or not, you get the same answer for the abundances, which is good. If you actually compute the cloud optical depths, the integrated cloud optical depths over the photosphere, we find that they're less than 1 for these two objects. So we can also check again to see if the chemistry we're getting is physically plausible. Are the combinations of the molecules we're getting reasonable? And the answer is yes. If we compare that to equilibrium chemistry calculations, we find that these bars, these vertical colored bars, are what we're retrieving from the data compared to what we would predict from a chemical model, equilibrium chemistry along the thermal profiles. We find that the answers are consistent. We're not getting bogus combinations of molecules. Some conclusions from this little investigation that the clouds seem to be negligible for these two objects and that the molecular abundances are reasonable. Okay, what about our benchmark scorecard? How did we do? So the red boxes or rectangles are the measurements and the uncertainties for this companion or the host star, and the little blob of probability is what we get for the brown dwarf from our retrieval. And we find that they're more or less consistent. This is kind of sitting at 2 sigma here for the C to O ratio, but overall fairly reasonable. One trick we have to do when converting the carbon to oxygen ratio of the atmosphere into the bulk carbon to oxygen ratio. Seriously, 3 minutes? Oh, wow, geez, I got to speed up. You have to account for the condensation of clouds, because you can lose oxygen in clouds. And so if we take the retrieved effective temperature and law of gravity, we can compare that to what evolution models would predict. And the spread represents the measured ages for the stars, and we find that we're getting consistent answers. And so we sort of agree. Our benchmark scorecard, we've more or less passed that test. And so now we want to unleash this technique on a variety of objects. So going back to this color magnitude diagram, focusing on these T dwarfs right here, specifically late T dwarfs, we're going to figure out what kind of properties we can learn about them. And T dwarfs are nice because they're predominantly cloud-free. And we're going to focus on a nice homogeneous set of data. This SPECS database put together by Adam Burgasser is a really nice uniform low-resolution database with hundreds up to 1,000 spectra of low-mass stars and brown dwarfs. And again, the temperatures of these objects are sort of analogous to a lot of the, sort of the peak in the temperature distribution of transiting planets from Kepler. So it's a useful temperature regime to understand. This is our sample of spectra, and the fits are good. Just want to show you, the residuals are small. I'm just going to skip through that because that's not interesting. Fits are super good, and we might be sensitive to the fact that some of these objects are unresolved binaries. And so we can back out what the thermal structures for each of these objects are. And great, what do we do with the thermal structures? Well, we can begin to address the static stability of the atmosphere and begin to do atmospheric physics on these objects. And so one useful diagnostic is the potential temperature. The potential temperature is the temperature that a parcel of gas would have if it were brought down from some layer in the atmosphere down to the bottom of the atmosphere, which is kind of arbitrary. And so if you do that, to our retrieved temperature profiles, you can back out these tornado-looking plots. And so the GCM people in the room should be able to appreciate what this is trying to tell us. But effectively, it's saying that the entire atmosphere is statically stable. Lines of constant potential temperature fall on an adiabat. If the potential temperature is increasing with decreasing pressure or altitude, that's telling you that your entire atmosphere is statically stable. It's happy. Entropy is what it should be. And so you can see there's a little region at sort of the top of the photosphere in these objects where that potential temperature begins to become constant again, which may be indicative of a secondary convection zone, for instance. So that's interesting. So we can do atmospheric physics with these types of results. Okay, now we can look at maybe what the trends and the abundances are with effective temperature. We don't really see any strong trends with these three gases, but an interesting trend that we would expect, something Mark pointed out long ago, is that the alkali metals are strongly dependent on temperature, and this is indicative of cloud formation in the atmosphere. And so we find this nice strong trend of increasing potassium and sodium abundance with temperature. So what's going on there? So here's an equilibrium chemistry calculation that takes into account the rain out of alkali metals into clouds. And what's happening is, as we're looking at hotter and hotter objects, we're sort of sliding along this chemistry, and so we're getting an increased column abundance of these alkali metal opacities. And so that's what we're seeing. So by looking at these objects over a wide range of effective temperatures, we're actually probing this cloud formation physics, which is kind of interesting. So we can also back out what the metallicities and carbon-oxygen ratios are for this sample of objects, and we find that it's more or less consistent with the carbon-oxygen ratios for the local stellar neighborhood, though depending on who you ask, these stellar abundances may be completely bogus. Apparently it's hard to get stellar abundances too, because like anything else, there's a whole load of assumptions that go into those, but we're more or less getting reasonable results. So I'll just quickly put up my summary here. So these data-driven retrievals are powerful tools for extracting atmospheric information. Again, I use brown dwarfs as an example because the data sets are high quality. We can back out reliable abundances. We learned interesting things about the atmosphere, about the static stability, about whether or not clouds exist, and we're able to probe some chemical processes happening in their atmospheres. And of course, there's always caveats. So I'll stop there and take any questions. Thanks. Magic. I don't know. Wind. Figure it out.
The pipe function is you get brown dwarf has spectral windows, so it's radiating through the window. As the air cools off, you've got to reach the number of windows, so it actually hurts production.
Yeah, we were having this conversation at lunch. Thanks. That's a good answer. You go. Yeah. That is the dark art of retrieval. So what we're doing is we're assuming radiative processes smooth out temperature gradients, or smooth out, we're going to have these bumps and wiggles. And so I impose a second derivative on the temperature, and that second derivative has to be minimum. So the data has to fight against that. So if the data is non-existent, you would basically get linear profiles. In the back. Yeah, so what's happening is we're sort of hitting where the tau equals greater than 1 due to the collision-induced H2 opacity, and we can't see below that where the convective region is happening. If we had higher resolution spectra, maybe we'd be able to see through some of those windows. But with this data, we cannot.
There still must be a deep convection.
Yeah, but we're just not probing it. I mean, physics says it should be there. We just can't. Like, the analogy I like to use is there could be dolphins swimming down there, and we wouldn't see them because they're below the photosphere. So it could be doing it. Yeah, higher up in the atmosphere. So the deep. No, so I'm not imposing any physics that says that it has to be an adiabat or radiative. The data is telling me this is the thermal structure, and that potential temperature was telling me at the upper region of the photosphere, it looked like it could be going back to stably stratified due to the explanation Mark gave. But in the deep atmosphere, you also go adiabatic again, but we just don't see that. Is that kind of answering your question? It's stably stratified everywhere, which means it's radiative. But I'm saying below the photosphere, you can't believe that.
What pressure below which you
It was like 5 bars. And the radiative convective boundary is sort of deeper than that. Back. Yeah, so what is physically self-consistent?
I guess I'm saying I don't have a good reason why you
Oh no, so what happens is, yeah, so they're zigzagging back and forth, but those are penalized because they're too wiggly, and so they get rejected. And so we're saying the physics that we're imposing on that is that radiative processes would smooth out those zigzags. So we started out with zigzags, and then the data combined with this imposition of smoothness relax those profiles to not be ziggy-zaggy. Does that answer your question? Yeah. Okay. Oh. Oh, sorry. Yeah, I'm picking on this side. No. The abundances are adjusting themselves as well. Yeah, it was hard to animate all of that, so I just picked the temperature. Well, they're kind of turning over. Yeah, right. There's a degeneracy with temperature and abundance. Yeah. Pascal. Yeah, so I'm assuming hydrostatic equilibrium, but I'm not imposing radiative equilibrium because, dynamics and stuff can happen. Yeah, radiative equilibrium is going to operate and things like that, but I don't want to impose that physics because I'm already biasing my answer if I do that. So I'm making simple assumptions that the propagation of flux through the atmosphere would care about, and that's things like hydrostatic equilibrium and the opacities and the temperature. So those are the things I'm interested in retrieving.
The fact that his solutions look so much like the grid models, and the grid models have all of that imposed, implies that the grid forward models.
So we're trying to validate the physics. We're trying to validate the physics that is assumed in self-consistent models. If you go to high enough resolution, we should be able to do that. This is all low res right now. But you can, there's this whole concept of this double diffusive convection that could potentially happen in brown dwarfs that could explain the color magnitude diagram. We could be sensitive to that in some cases with these spectra for L dwarfs. And you can fit the spectra, cloud-free atmospheres, invoking something like that. So in a sense, yes, you would be, but not microturbulence. Like in stars, we're not sensitive to that. You'd have to go to super high resolution. Yeah, if there's cloud formation, yeah, that will like Earth, that's going to change your adiabat. It's going to make it less steep. Yeah, so I assume dry potential temperature, but this is sort of circular. I wasn't finding that I needed clouds, so there should be no moist adiabat. It's dry. Marco. I don't, which is why I'm using MKO. Do I include what? Yeah, I'm the sodium and potassium. I'm just the alkali metals, sodium and potassium. So they're in their elemental form. Some of it is going into like salt sulfide and KCl clouds. Yeah, they could exist. We're just finding that they're not in a substantial enough mass abundance to contribute to the opacity, at least in this example.